Welcome back to the deep dive. Today we are stripping away the Hollywood gloss, the neon lights, and the techno thriller soundtracks from a word that I think everyone uses, but very, very few people actually understand.
And that word is hacker.
Hacker. It is a word with a serious identity crisis.
Maybe the biggest identity crisis in the English language.
It really is. You say hacker to someone at a coffee shop or your parents or even a random person on the street, and what do they picture?
They picture a criminal.
Immediately, they see a guy in a hoodie sitting in a dark basement.
Always a basement.
Always a basement, never a sunroom typing furiously to steal credit card numbers or shut down a power grid or drain a bank account. It's just, it's become synonymous with cyber criminal.
It implies malice.
It does. But today, we are looking at a source that argues that this definition is not only wrong, it's actually insulting to the history and the spirit of the term.
We are diving into Hacking, The Art of Exploitation, 2nd edition by Jon Erickson. And I'm really glad we're doing this one.
Me too.
Because this book is a classic. It's not just a technical manual. It's a manifesto.
It really is. And I want to set the stage immediately for everyone listening. This is not a how to commit crimes handbook.
Right. Very important distinction.
We aren't here to teach you how to steal your neighbor's Wi-Fi password or break into a government server. Erickson's premise and the mission for this deep dive is much more profound. We want to take you from being a person who simply uses software or even a standard programmer who writes code and just kind of hopes for the best.
Yeah, crosses their fingers.
To someone who understands the DNA of the machine.
Right. Think of it this way. Most people drive the car. They know how to steer, they know gas and brake.
That's me.
Some people, the mechanics or, the standard programmers, they know how to change the oil or replace a belt.
Okay.
Erickson wants you to be able to rebuild the transmission blindfolded.
While the car's moving.
While the car's moving. That's the level we're aiming for.
I love that image. But before we get into the transmission, the bits, the bytes, the registers, the raw electricity of the thing, we have to start with the philosophy.
We have to.
Because the book opens with this mental puzzle that I think perfectly encapsulates what a hacker actually is. And I love this because it has absolutely nothing to do with computers.
It's the math problem.
Yeah.
This is a perfect litmus test for the hacker mindset.
Okay, listener, I want you to play along with us here. Seriously, try to solve this in your head as we go. You have 4 numbers, 1, 3, 4, and 6.
And you have to use each number exactly once.
Exactly once. You can use any of the basic math operations, addition, subtraction, multiplication, and division. The goal is to make them total 24.
And the constraints are key here. You can't combine numbers to make like 13 or 46.
Yep.
You have to use the digits individually as single integers, and you must use all of them.
So I sat down with this, I looked at it, and my brain immediately went to the standard integer math I learned in grade school. I'm thinking, okay, 4 times 6 is 24.
Boom, done.
Done. But I have a 1 and a 3 left over.
And that's the trap.
Right. If I multiply by 1, I still have the 3. If I add the 1 and 3, that's 4. And if I add that to the 24, I'm at 28. I've overshot.
Way over.
So I try again. I think, okay, 3 times 6 is 18.
Okay, you getting closer.
I have a 4 and a 1 left. 4 plus 1 is 5. 18 plus 5 is 23. So close. But it's not 24.
You hit a wall. You hit a wall because you are thinking like a user of math.
Right.
You're using the standard, obvious paths that have been drilled into you since 3rd grade. You're thinking in these rigid blocks.
It genuinely felt impossible for a minute. I was convinced there was a typo in the book.
I think everyone feels that way at first.
So how does a hacker solve this?
A hacker looks at the tool set, the operations, addition, subtraction, multiplication, division, and they ask, what are the properties of these tools that aren't immediately obvious? What are the edge cases?
Okay.
The solution requires you to embrace something most people try to avoid. Fractions.
Fractions. The bane of my elementary school existence.
The solution is 6 divided by,
Okay.
parentheses 1 minus 34.
Okay, let's parse that slowly. We have 1, 3, 4, 6. Inside the parentheses, we have 1 minus 3/4.
Which leaves you with 1/4.
Right, 14. So now the problem simplifies to 6 divided by 14.
And basic algebra teaches us, even if we've forgotten it, that dividing by a fraction is the same as multiplying by its reciprocal.
So dividing by 14 is the same as multiplying by 4.
So 6 times 4 is 24.
That is. It's annoying, but it's brilliant.
It is.
It feels like a cheat code.
It feels like a trick, doesn't it?
Yeah.
But notice something crucial. You followed the rules perfectly.
I did.
You used every number once. You used standard operations. You didn't invent new math, But you used the rules in a way that the person setting the problem or the average person solving it didn't anticipate.
That's the key.
That is the definition of a hack. It is following the rules of the system so strictly and so creatively that you produce an unintended result.
Unintended result. I want to stick a pin in that phrase because that seems to be the theme of this entire book.
So,
Hacking isn't about breaking the rules. It's about understanding the rules better than the person who wrote them.
precisely. It's about finding the latent potential in a system. And this spirit didn't start with computers. Erickson traces the lineage back to the late 1950s at MIT.
Right, the Tech Model Railroad Club.
The Railroad Club.
Trains. I love that the original hackers were playing with toy trains.
Well, toy might be underselling it a bit.
Hmm?
These guys were obsessed with the system. They had this massive donation of old telephone
To the
equipment.
junk, right.
Total junk.
Yeah.
Relays, switches, solenoids, mostly stuff from the phone company. And they used this junk to build an incredibly sophisticated system to control the tracks.
What could it do?
They could dial numbers to switch tracks and control train speeds across this massive layout. They were programming the physical world before they were programming screens.
They were essentially building logic gates out of telephone scraps.
Exactly. And they called this inventive use of junk hacking. It was a verb. I hacked this circuit together.
Ah, so it was a process.
It was a process. And there's a vital metric they used to judge each other's work. Elegance.
Elegance. Talk to me about that. Because usually when we think of engineering, we just think functional. Does it work?
Yeah.
Yes. Okay, move on.
For a hacker, does it work?
Mm-hmm.
Is the bare minimum. The real question is, how well does it work? It wasn't enough just to make the train switch tracks.
Right.
If you could build a circuit that did it with 5 fewer switches than the other guy, your hack was better. It was about mastery and efficiency.
It's an aesthetic.
It's totally an aesthetic. It's the difference between a milk crate holding your books and a handcrafted mahogany bookshelf. Both whole books. One is art.
So somewhere along the line, this term hacker, which meant a master of the machine, an artist of efficiency, a creative problem solver, got hijacked.
Completely hijacked.
How did we get from the model railroad club to the criminal in a hoodie narrative?
Well, as the culture moved from model trains to mainframes and then to the internet, the power of these skills grew exponentially.
Of course.
If you understand the system better than the administrator, you can gain access. That's just a fact. Some people use that access to explore, to learn, to look around.
The curious ones.
And others used it to steal data, delete files, or crash systems.
Yeah.
The bad apples, as you said.
And the community actually tried to distance themselves from that.
Oh, they tried very hard. They coined the term cracker for the malicious ones, the people breaking copy protection or stealing data for profit.
I remember seeing Cracker in old forums back in the 90s, but it never really hit the mainstream news. You never saw a CNN headline saying, "Bank robbed by Cracker"?
Yeah. It's a marketing problem, honestly.
You think?
Cracker sounds like a snack food. It sounds brittle. Hacker sounds mysterious. It sounds edgy. It involves a hack, a cut, a chop. The media latched onto hacker because it sold newspapers, and the distinction was lost to the public.
So the original meaning was just erased?
In the public eye, yes. But inside the community, the hacker ethic is still very real.
Let's talk about that ethic. Because if we are going to reclaim the word, we need to know what it stands for. Erickson highlights a few pillars of it. One is this idea of meritocracy.
It's one of those beautiful parts of the culture.
Right.
And something the corporate world could learn a lot from. In the book, he mentions Peter Deutsch.
Right.
In the MIT days, Peter was 12 years old.
12 walking into an MIT research lab.
And not just walking and touching the multi-million-dollar equipment.
Yeah.
And the researchers didn't kick him out.
That's amazing.
They didn't ask for his PhD. They didn't ask who his father was. They saw that he understood the TX0 computer better than some of the grad students.
So they let him work.
So they let him hack. Ideally, hacking is blind to age, race, gender, and credentials.
Yeah.
It only cares about the code. Does it work? Is it elegant? If the answer is yes, you belong.
That's incredibly pure. It's refreshing. But the reality is that this pure curiosity often runs headfirst into the real world, and specifically the legal world. Erickson spends some time discussing the tension between the spirit of hacking and the letter of the law.
Specifically, laws like the DMCA, the Digital Millennium Copyright Act. This law, broadly speaking, makes it illegal to reverse engineer copy protection or encryption.
Which essentially makes it illegal to figure out how a device you own actually works, right? If I buy a book, I can read it. But if I buy an ebook and I want to see how the file is structured.
You are crossing a legal line. It criminalizes curiosity.
Wow.
There's a famous case mentioned in the book, Dmitry Sklarov. He was a Russian programmer, very talented. He figured out how Adobe's ebook encryption worked.
Okay.
He realized it was flawed.
Hmm.
He wrote a program to bypass it, purely as a technical proof, essentially saying, look, this lock is broken.
He was pointing out a vulnerability, a public service almost.
You'd think so. He presented his findings at a conference in the U.S., effectively sharing knowledge, and the FBI arrested him.
For doing math, for solving the puzzle.
Basically, Erickson uses a fantastic analogy here that really drives the absurdity home. Imagine if someone invented a copy protection scheme based on Pig Latin.
Okay, Pig Latin. Taking the first letter, moving it to the end, adding A.
Right. Hacker becomes hacker. Now, imagine the government passed a law saying it is illegal to discuss how to translate Pig Latin back into English because that bypasses the protection.
You're not stealing the content.
No. You aren't stealing the book. You're just explaining the linguistic rule. That's what happened to Sklarov. He explained the grammar, the encryption, and he went to jail for it.
That effectively freezes innovation, doesn't it? If you can't discuss the flaws, you can't fix them.
Exactly. It stops the coevolution. Security is like biology. Think of the cheetah and the gazelle.
Predator and prey.
The cheetah gets faster to catch the gazelle, so the gazelle has to evolve to be faster to survive, which forces the cheetah to improve again. They make each other better.
I see the parallel.
If you jail the hackers, the cheetahs, the gazelles, the security systems get lazy. They stop evolving. You end up with weak infrastructure because no one is allowed to test it.
So we need the hackers to keep the defenders honest.
We need that pressure. The system needs that pressure to improve.
That is a compelling argument. But if we want to be part of this evolution, if we want to understand the machine well enough to test it, we have to speak its language.
Yes.
And this is where the book shifts gears from philosophy to hard technical skills. Erickson focuses heavily on one language, C.
The C programming language. And I can hear some modern developers groaning right now.
Why C? It's ancient.
It's from the 70s. Why not Python? Why not Rust? Why not JavaScript?
It's a fair question. Why are we learning the Latin of programming languages in 2026?
Because Latin explains the roots of the modern languages. If you know Latin, you understand Spanish, French, and Italian structure on a deeper level. But more importantly, C allows for what we call direct memory manipulation.
What does that mean in practice?
Think of Python or Java like a modern car. A Tesla, maybe. It has lane assist, automatic braking, traction control, and a computer that stops you from doing anything stupid.
It's safe.
It's safe. It handles the details for you. C is an engine on a go-kart with a manual throttle cable and no brakes. You can reach out and touch the spinning gears with your bare hand.
And if you touch the wrong gear...
You crash.
Yeah.
Hard. You can literally crash the entire program or the operating system.
Yeah.
But to exploit a system, you need that access.
You need to be able to touch the gears.
You need to be able to manipulate the raw memory. Python hides that from you for your own good. C serves it up on a platter.
Let's walk down the hierarchy of how a computer understands language, because this was a big light bulb moment for me in the book.
Yeah, this is fundamental.
We start at the top with high-level languages.
Right. This is your C code. It looks like English. You write if, x, ipsofas,
Yeah.
hash and do something. It's readable.
Yeah.
A human can look at it and understand the logic.
But the computer doesn't speak English. The CPU doesn't know what an if statement is.
Not at all. So we run it through a compiler. The compiler is a translator. It takes that English-looking text and translates it into assembly language.
Assembly. This is where it starts to look cryptic.
It's the bridge. Assembly is specific to the processor you are using. If you have an Intel chip, you speak by 86 assembly. It's a series of mnemonic short commands. MOV, ADD, JMP.
Just JMP, ijump.
Yes.
Yeah.
It's giving direct commands to the CPU. Move this data here, add these two numbers, jump to this other instruction. It's very granular.
And then below assembly, what's the final layer?
Machine language. The raw truth, this is just numbers, ones and zeros, usually represented in hexadecimal base 16 because humans can't read 32 zeros in a row without going cross-eyed.
And this is the only thing the computer actually runs.
The only thing.
And here is the matrix moment Erickson describes. He says that most programmers stop at the source code. They think the source code is the program.
But the computer never sees the source code. It only sees the binary, the a.out file. The compiler might have optimized things. It might have rearranged your logic to make it faster. It might have removed variables you didn't use.
So there is a gap between what I wrote in C and what is actually executing in the CPU.
And that gap is where the exploits live. A hacker doesn't trust the source code. A hacker looks at the binary. They look at the reality.
So the source code is a map.
And the binary is the territory. If you want to find the secrets, You have to explore the territory.
To see that reality, we need a tool. We can't just squint at the hard drive and see the magnetic poles flip.
No, we need a microscope.
And Erickson introduces GDB.
The GNU debugger. This is the hacker's microscope.
I liked the analogy of the magician here.
It's perfect. Imagine watching a magician perform a sleight of hand. He makes a coin disappear. It happens too fast to see. You know it's a trick, but you can't spot the move. GDB is a universal remote control for the universe inside the computer. It lets you pause the magician, walk up on stage, look up his sleeve, check his pockets, count the cards in the deck, measure the angle of his wrist, and then hit play for 1 millisecond to see where the coin moves.
It freezes time.
It freezes time and lets you inspect the state of the universe. You can change values while time is frozen.
Seriously?
Oh, yeah. You can take the coin out of his pocket and put it in his other pocket, then hit play and watch him get confused.
That is an incredible amount of power. And when we use GDB to look up the CPU's sleeve, what do we find? We find registers.
Registers. These are crucial to understand. The CPU is a calculator, but it doesn't have a hard drive in it. It's a processor, not a storage unit.
So it needs somewhere to hold the numbers it's working on.
Exactly. It needs hands to hold the numbers it is currently working on. Those hands are the registers.
Okay, let's meet the cast of characters. We have the general purpose ones.
EAX, EBX, ECX, EDX. These are the workhorses. EAX is the accumulator. It's used for math and storing the return value of a function. ECX is often a counter for loops. These hold the variables while the math is happening.
But the ones that really matter for hacking, the ones that let us break the system, are the pointers.
The pointers tell the computer where it is. You have the stack pointer, ESP, and the base pointer, EBP.
What do?
They define the workspace. They define the room the code is currently operating in. They keep track of where the temporary data is stored.
But there is one register that rules them all, the EIP.
The instruction pointer.
Why is the EIP the holy grail? Why does every hacker want to control this specific register?
Because the EIP tells the CPU what to do next. It is literally a finger pointing at a memory address saying, execute the code living here.
And then it moves on.
Then it moves to the next line. Now execute this. It drives the train. It's the program counter.
So if I can change the value inside the EIP...
You move the finger, you can tell the computer, don't run the next line of the antivirus software. Instead, jump over here to this piece of memory where I wrote some malicious code and run that.
Controlling the EIP is controlling the mind of the computer.
That is the game. Everything we discuss regarding buffer overflows and format strings is really just different ways to try and overwrite that one register. If you control EIP, you own the machine.
Now, to understand how we overwrite it, we have to understand the landscape it lives in. We have to talk about memory. Erickson describes memory in a very visual way.
Yes. Visualize memory as a long, single row of houses. A linear street. House 1, House 2, House 3.
And each house holds
1 byte of data. Just 1 byte.
Okay, simple enough. But there is a very weird rule in this neighborhood called endianness. Specifically, little endian. This tripped me up when I was reading. It felt wrong.
It trips everyone up. It's completely counterintuitive. Most Intel processors, which is likely what is in your laptop right now, are little endian. It means they store multi-byte numbers backwards.
Give us an example. Let's make this concrete.
Okay. Let's say you have the number 0 by 45 C7 in hex. In our minds, 45 is the big end, the most significant byte, and C7 is the little end, the least significant byte.
Right.
Humans write it 45 C7, but the computer stores it in its memory houses as C7 in the first house and 45 in the next house.
It puts the little end first.
Right. It's like writing hello as Ali.
Why? Is the computer just trying to be difficult?
It's actually for efficiency in electrical engineering terms, how the circuits do math. But for us, the software people, it's just a headache we have to deal with.
So if you're looking at memory in GDB...
You will misinterpret every number you see if you don't know this. You'll see 0804 in memory and think the number is 804, but it's actually 04 or 08. You have to flip it in your head.
And if you are trying to write an exploit...
This is absolutely critical. If you want to overwrite the EIP with a specific address, say 0x dead beef, you have to write it into your exploit code as EFBEADDE. You have to feed the computer the bytes in the order it expects. If you write it forward, the computer reads it backward, and your exploit jumps to a random location, crashes the app.
So you have to think in reverse.
You have to think like the machine thinks.
Okay, so we have this street of memory, but it's zoned. It isn't just a free-for-all. It's divided into segments.
5 main segments. And knowing which is vital because they all behave differently.
Let's run through them quickly. First, the text segment.
This is the code itself. the machine language instructions. It's usually marked as read-only.
Why?
If you don't want the program rewriting its own instructions by accident, that would be chaos.
Then data and BSS.
These are for global variables, variables that need to be accessible from anywhere and stick around for the whole life of the program. Data is for things you gave a value to, like int score equals 0. BSS is for things you didn't, like int score.
But the real action, the place where the magic happens, is in the last two, the heap and the stack.
The heap and the stack. They sound like a comedy duo, but they are the workhorses of dynamic memory.
The heap is messy.
It's the Wild West. It's for dynamic memory. If you don't know how big a file is until you open it, you need to ask for space for it. You put that in the heap.
And it grows in a specific direction.
It goes down toward higher memory addresses.
And the stack.
The stack is structured. It's the scratch pad. It's for temporary things, local variables, function calls, and it grows up toward lower memory addresses.
They grow toward each other.
Yes, like a stalactite and a stalagmite in a cave. If they ever meet, you have run out of memory and the program crashes. But usually there's a big gap of unused memory between them.
Let's double-click on the stack. Erickson spends a huge chunk of the book here. Why is the stack so important?
Because the stack is where the context lives. Every time a function is called, the computer uses the stack to remember who called me, what are my variables, and where do I go back to when I'm done.
The book uses the analogy of a stack of plates in a cafeteria.
It's perfect, or beads on a string. It's Philo first in, last out. You push a plate onto the stack. To get the one underneath, you have to pop the top one off. You can't just pull a plate from the middle without breaking everything.
Let's visualize a stack frame. This is what gets built when we call a function. Let's say main calls test function. What exactly gets pushed onto this stack of plates?
Okay, imagine we call a test function with two numbers, say 10 and 20. The first thing that happens is the computer pushes those arguments, the 20, then the 10 onto the stack.
In reverse order.
In reverse order, which is a whole other historical detail.
Yeah.
But then, and this is the most critical part of the entire episode, it pushes the return address.
The return address. This is the bookmark.
It's the saved EIP. It's the CPU taking its finger at the EIP and writing down on a piece of paper, I was at line 50 in Maine, and putting that paper on the stack. It remembers where we came from, so it knows how to get back.
Okay, so the return address is sitting on the stack. What goes on top of it?
The save frame pointer, SFP, which is just organizational bookkeeping to remember the last function, stack, and then the local variables.
The local variables. So if my test function has a text buffer, say a place for me to type my username, that buffer is sitting on the stack.
Yes, it's allocated right there on top of everything else.
And physically, in memory, that buffer is sitting right next to the return address.
They are neighbors on that long street of houses. There are no walls. There are no fences. Just byte after byte.
This is the setup for the most classic hack in history, the stack buffer overflow.
It's simple physics. If you have a bucket that holds 10 bytes of water and you pour 20 bytes into it, the water has to go somewhere.
Right.
In memory, it doesn't spill on the floor. It spills into the next address. It overwrites whatever was there.
So if I am the user and the program asks for my name and the buffer is, say, 16 bytes long, and I type a name that is 500 characters long.
Your name fills up the 16-byte buffer. Then it keeps going. It spills over and overwrites the save frame pointer. And if you keep typing, it overwrites the return address.
I have washed away the bookmark.
You've replaced the bookmark with your own data. So when the function finishes and tries to return, the CPU looks at that spot on the stack and says, where do I go? But instead of the original address, it sees your data. It sees the letters of your long name.
And if my data happens to be a valid memory address?
The CPU jumps to it. No questions asked. It's just a number to the CPU. It will blindly execute whatever is at that address.
So if I carefully craft my lawn name to include the address of my own malicious code, which I've also stuffed onto the stack.
You have hijacked the EIP. The CPU executes your code. You have taken over the program.
That is terrifyingly simple in concept. It's like rewriting the GPS coordinates while the car is driving.
It is. But getting it to work is an art. It's incredibly precise. If you're off by 1 byte, the CPU jumps to the wrong place, hits a dead end, and the program just crashes.
And that's a segmentation fault?
A seg fault. That's the machine telling you you tried to touch a house you don't own.
Which brings us to another key mindset shift. A normal user sees a crash and gets annoyed. Stupid app, it crashed.
Yep, they just restart it.
A hacker sees a crash and gets excited.
A crash is a clue. A crash is a signal from the machine. It means you touched something sensitive. It means your input affected the memory structure enough to break it.
So it's a success, in a way.
It's a huge success. If you can crash it, you can potentially control it. You just need to refine your aim.
So hackers spend a lot of time crashing things on purpose.
Hours, days, they fuzz the input, throwing random garbage at the program just to see where it breaks. Once it breaks, they open GDB and look at why it broke. Did I overwrite the EIP with 0 by 414144141, which is the hex for AAA?
Ah, so you send a long string of A's.
Exactly. If you see that EIP is now 4 A's, you know you control it. Now you just need to replace the A's with a real address that points to your exploit.
We've talked a lot about the stack. We also need to touch on the heap, because not everything lives on the stack.
No, the stack is for small, temporary things. The heap is the Wild West of memory.
Why Wild West?
The stack is automatic. The computer manages pushing and popping. You call a function, it pushes. You return, it pops. The heap is manual. You, the programmer, have to explicitly ask for memory.
This is malloc.
Malloc, short for memory allocation. You say, hey, computer, I need 50 kilobytes to store this image. The computer finds a free spot on the heap and gives you a pointer to it.
And because it's manual, you have to promise to clean up after yourself.
You have to call free. If you don't, that memory stays occupied forever, even after you're done with it. That's a memory leak. If you leak enough, the computer runs out of RAM and crashes.
But the vulnerability here is often about how the computer manages those chunks of memory.
Right. The heap manager has to keep a little notebook. It keeps track of which chunks are free and which are used. It stores this info in headers right next to the data. Again, neighbors.
Neighbors without fences.
Exactly. If you can write past the end of your heap buffer, you can overwrite the header of the next chunk. You can trick the memory manager into thinking a used chunk is free, or a free chunk is bigger than it is. It's a different kind of memory corruption.
And there's the use after free vulnerability I've heard about.
That's a big one. It's exactly what it sounds like. You free a pointer, but you forget to delete the pointer itself. Later, the program tries to use that pointer again.
But the memory it points to has been given to someone else.
Right. Now you are reading or writing data that belongs to a completely different part of the program. It's chaos. You're corrupting unknown data structures.
It sounds much harder to exploit than the stack.
It is. Infinitely harder. The heap is dynamic. Things move around. The stack is predictable. But heap exploitation is where the modern dark arts are. It's complex, but the principle is the same. Find a way to corrupt control data.
Speaking of control, a program isn't an island. It has to talk to the world. It has to read files, write to the screen, take input. We need to talk about file access.
Input, output, or I/O. In Unix and Linux, which is the environment this book lives in, there is a golden rule. Everything is a file.
Everything.
Everything. A text document is a file. Your keyboard is a file. Your screen is a file. A network connection is a file. Even the memory itself can be treated as a file. It's a powerful abstraction.
And the OS tracks these with file descriptors,
Which are just numbers, integers.
I was surprised by how simple this was. I expected complex IDs like, I don't know, UID 459X.
Nope. It's wonderfully rudimentary. Every program starts with 3 open files by default.
Which of?
Xyla is standard input, statin, usually your keyboard. 1 is standard output, usually your screen. And 2 is standard error stutter, where error messages go, also usually your screen.
So if I open a new document, what number do I get?
The OS just gives you the next available number, usually 3. Then the next one is 4, then 5. It just counts up.
And you use that number, that integer, to tell the OS write to file 3.
Exactly. The system call would be something like write 3, buffer, size. It's very direct.
But when we open these files, we have to tell the OS how we want to use them. Read only, write only, append. And this brings us back to that hacker math. We use flags.
Bitwise flags. This is another area where understanding binary is non-negotiable.
Imagine a row of light switches on a wall.
Perfect analogy.
Yeah.
Each option is one switch, one bit. Let's say bit 1 is read access. Bit 2 is write access. Bit 3 is create if not exists.
Each one is a power of 2.
Right. 1, 2, 4, 8, and so on.
And if I want to open a file for writing and create it if it doesn't exist?
You flip both switches on. In code, you use the OR operator, which is the pipe symbol for area out. You'd say RNLY, O create.
And the computer takes the binary for write and the binary for create and smushes them together?
It overlaps them. It's not adding them like math,
Yeah.
1 + 2, 3. It's
Yeah.
ORing them.
Yeah.
If either switch is on in a given position, the result is on. It's a very compact, efficient way to pass a complex set of instructions in a single integer.
It's elegant.
It is. And understanding this allows hackers to manipulate permissions. If you can find a way to flip a bit in the arguments passed to the open system call, you might turn a read-only file access into a write access just by changing a 0 to a 1.
We've covered a staggering amount of ground here. We've gone from the philosophy of the MIT Railroad Club to the intricacies of the stack to the heap to bitwise logic. It's dense.
It is dense. This is not light reading. Erickson's book is a workout for your brain.
But remember the goal. We aren't trying to make you a kernel developer in 60 minutes.
No, not at all. The goal is to demystify the magic.
Right. When you see a news story about a zero-day exploit or a buffer overflow that took down a bank, I don't want you to think it's wizardry performed by a warlock in a hoodie.
I want you to visualize the stack of plates. I want you to visualize the water spilling over the edge of the bucket and washing away the return address bookmark.
It takes the fear out of it. It's just physics.
It's digital physics. It's putting matter data into a space not designed to hold it and watching the structure collapse in a predictable way.
And that leads me to a thought I wanted to run by you, a bit of a synthesis of all this. If these vulnerabilities, these buffer overflows, these pointer errors are just a natural consequence of how the stack and the heap work, are they bugs or are they features?
That is the provocative question. That's the hacker mindset right there.
Right.
Erickson argues that they are simply properties of the architecture. The computer's doing exactly what it was told to do. It was told to copy data from here to there. It copied it. It wasn't told to stop at 10 bytes, so it didn't. It's not broken. It's just obedient.
So can we ever truly secure these systems?
That's the million-dollar question. As long as we use languages like C that allow for this kind of direct manual access, and as long as humans are writing the code and making math errors or off by one errors, there will be gaps.
There will be unintended results.
There will always be unintended results.
Yeah, which means there will always be hackers.
And we need them. We absolutely need them. Remember the cheetah and the gazelle. If we didn't have people obsessed with finding these unintended uses, our systems would be incredibly fragile. We would have security by obscurity, which is no security at all.
We need the breakers to help us build better walls.
Exactly. The attackers make the defenders smarter, and the smart defenders make the attackers more creative. It's an arms race that makes everything stronger.
So for the listener who has listened to this and thought, I want to see the Matrix, I want to look up the magician's sleeve, what is the next step?
Don't just read about it, do it. That's the only way.
Put your hands dirty.
Get a Linux virtual machine. It's free. Download GDB. It's free. Get the source code from Erickson's book, or write your own simple C programs.
And don't just read the code.
Don't just read it. Compile it. Then run it in GDD. Step through it, instruction by instruction. Watch the EIP register change. Watch the stack grow and shrink. Change a value in memory and see the program crash.
So cause the crash on purpose.
Cause the crash. Understand the crash. Be the one with the microscope.
It sounds like a rabbit hole.
Oh, it's the best kind of rabbit hole. Once you see the binary reality underneath the code, you can't unsee it. You'll never look at a loading bar the same way again.
You'll be thinking about memory allocation.
You'll always wonder, what's happening on the stack right now?
I think I'm going to go download a hex editor and stare at some bytes. Thank you for guiding us through the machine.
My pleasure. Happy hacking.
And to our listeners, thanks for diving deep. Stay curious, break things to learn how to fix them, and we'll see you on the next one.